All right, we're going to continue to look at section 6.4 and how we can calculate work using variable forces and integration. So what we had talked about previously is that work is going to be equal to the definite integral from a to b of a force function. And so I'm just reminding you of the basic formula that we use to calculate work. A to b is an interval over distance instead of time. So this is a distance interval. And then capital F is our variable force equation or function, however you want to think of it. Okay, so that's kind of our basic idea. That's what we were using yesterday. And now we're just going to look at another type of work situation. All right, and that is going to be dealing with springs. All right, and so the idea is if I try to draw you guys a spring, all right, if you think of that as a spring and it's in its rest position, we're not compressing it, we're not stretching it out, but there's our spring. And the idea is if we were to grab hold of the end and extend it, or if we were to grab hold of the end and compress it, that requires work. We would have to do work. We have to apply force over a distance, so therefore work, to either extend the spring or compress the spring. All right, and to calculate the work done, we use something called Hooke's law, which says that the force required is equal to a spring constant that we traditionally call little k, multiplied by x, where x is measured in meters and k is just a scalar, meaning it doesn't have any units attached. There's no seconds, there's no newtons, there's no numbers attached to k, but that's called the spring constant. And the idea is every spring is going to have its own constant. The spring that you might have in a ballpoint pen has its own constant. The spring on your garage door opener has a much different spring constant. So the spring constant is essentially what dictates how much work is going to get done, either stretching a spring or compressing a spring from its at-rest position. All right, so since we know work now is going to be the definite integral from a to b of f of x dx, f is again the force function, then specifically for springs, the work done is going to be, we can just replace f of x, capital F of x, with what it's equal to, which is k times x dx. So we can just replace our force function when we're dealing with springs with k times x. Okay, and as we go through our examples, you'll see that essentially the trick becomes being able to determine the value for k. The first example I'll do for you guys, I'm just going to tell you what the value of k is, but then in the next two examples, I'm going to make you help me find the value for k. We're going to have to go through that work. Okay? So there's the kind of the extension beyond our basic work formula when we're dealing with springs. Okay? So let's take a look at an example. This one will be very easy. What I'm going to ask you to do is take a spring constant. Here I'm going to give you a spring constant of 8. Again, no labels attached. And then what I'm going to ask you to do is find the work done to move the spring from x equals 1 meter to x equals 6, oops, sorry, I forgot the equal sign there. X is equal to 6 meters. Okay, and again, this one's going to be actually quite easy because sorry about that, hit the wrong button. There it is. Because I'm telling you what the spring constant is. So we can almost immediately get to our work equation, right, by taking the integral from 1 meter to 6 meters and we include our spring constant, 8 multiplied by x dx. And that's all there is to it. We were given the spring constant, so we just have to replace little k with 8. And now, of course, the integration is incredibly simple for you guys. We add 1, divide by the new, and then we'll be doing fundamental theorem from 6 down to 1. A little bit of canceling here. So what we'll have is 4 times 6 squared minus 4 times 1 squared. And let me punch out the math so I don't get it screwed up here. 4 times 6 squared minus 4 times 1 gives me a value of 140. And since we're in the metric system, please notice we were in meters. That means then that we'd be doing 140 joules of work. Okay? Like always, feel free to pause the video if you need to get something down, if you feel it's necessary to put into your notebook. Probably don't need this first one. One of the next two would probably be a good idea though. All right, so let's try another one. Okay, and got a little bit to write out here, just kind of get you the setup. First, we have a spring which has a natural, learn to spell, has a, there it is, natural length of 0.6 meters. It requires 40 newtons of force to stretch it to 0.8 meters. The question then is, how much work is done to stretch it from the 0.7 meter mark to the 1.0 meter mark. Okay? Again, feel free to pause the video if you want to jot down all of that work, but I'm just going to launch right into it. So to calculate the work done, right, what we're going to have to do is integrate the spring constant times x dx. So the value we need right here in this spot, let me put a highlighter on it. The value we need in this position right here is little k. We need little k in that spot. Okay, now to find that, we have our relationship called Hooke's law, which says the force applied to a spring is equal to the spring constant multiplied by the distance. All right, and in the given piece of information in the middle sentence, we actually have this 2 out of the 3 of these pieces. We can see how much force is required. It says it requires 40 newtons of force to stretch the spring to 8 meters. Now, this is a mistake, so don't write this down, but it'd be real easy to put in 0.8 because you're seeing in the problem, let me highlight this as well, you're seeing where it says 0.8. But that's not correct because if I slide this over a little bit so I have some room to work, the spring originally has a length, right? The at-rest state, the spring has a length of 0.6 meters. Now our force, our 40 newtons of force, are required to stretch that to 0.8 meters. So how much have we actually stretched the spring? We haven't stretched it 0.8 meters, right? We essentially have to calculate how much distance we've stretched the spring, and in this case that would be 0.2 meters. So we're not going to use 0.8 for x. What we're going to do instead is use 0.2 for x. It's how much distance over that or how much distance does the spring move using 40 newtons of force. All right, and then therefore, of course, we can solve for k, divide both sides by 0.2. Pardon me. And so the spring constant for this situation would be 200. So now I could back up to the rest of the problem, replace k with 200, and of course, oh, I'm sorry, I almost forgot one thing. We also have to find the limits of integration. Once again, it'd be real easy to put in 0.7 to 1.0 because those are the values shown in the problem. But again, we have to make the calculation in terms of from its natural length. So it's not going to be 0.7 and 1.0. It's the distance from its natural length. Again, the natural length is 0.6. So when we're at 0.7, we've already stretched it 0.1 of a meter. And when we finish at 1.0, that means we've moved it 0.4 meters. So this would then be the correct setup to calculate the work. The definite integral from 0.1 to 0.4 of 200x dx. Now, of course, the rest of this is just simple mix simple. We add 1, divide by the new. I'm going to do a little canceling there. And then we just simply put in our two values and we're set to go. So we'd have 100 times 0.4 squared minus 0.1 squared. What is that? That's going to be a 0.16, I think. That's going to be a 0.01. 0.16 minus 0.01 is 0.15. I hope I'm doing that okay in my head. And 100 times 0.15 is 15. Once again, all of these problems we're going to be in the metric system. So we're going to be at 15 joules. 15 joules of work to get that done. Okay? All right. And I'll shrink this down in case anybody needs to pause the video and look at any part of that in total. Oop, try that again. There it is. All right, so feel free to pause if you need to look through any part of that. All right. Otherwise, though, I'm going to go on to one more example, one more spring example for this video. Okay, and the setup's going to be the same. We're going to have to find the spring constant once again. All right, and so here's the problem. You need to exert 120 newtons of force to compress the spring 120 centimeters. Okay, I'm intentionally putting in a set of parentheses there. Question, how much work is done when we compress the spring from its natural length to 65 centimeters. Okay. All right. And the reason I left the parentheses in there, and doggone it, I meant to do it at the very end as well. Let me get rid of the question mark for just a second. And the reason I left those is we got to make sure that we always change any centimeters to meters. The force equation is only set up if we're measuring in meters. So the 120 centimeters would then become 1.2 meters. And the 65 centimeters would become 0.65 meters. Okay, and again, what we're going to have to do is first find the spring constant. So here's our Hooke's law. We insert how much force is required, 120 newtons. We insert the compression distance, 1.2. So when we divide both sides by 1.2, we get a spring constant value of 100. And then the work done, to answer the question, is going to be the definite integral from its natural length. So we haven't moved it anywhere. It was at its natural length. It hadn't moved. And then we're going to move it 0.65 meters. Okay? So we just need the spring constant, which we just found, multiplied by x dx. All right, and that would be the complete setup. So the integration, obviously very easy, just add 1, divide by the new. cancel a 2 top and bottom, and then insert 0.65 and subtract, then insert 0. So I'm going to need a little calculator help on this one because I don't know what 0.65 squared is. So 0.4225, obviously minus 0, and then multiply by 50, and we get about 21.125. I guess we don't need all those decimal places, but anyway. So we'd have approximately 21.1 joules of work. And once again, I'll shrink this down so you can see the whole thing. There we go. If you need to pause the video and jot anything else down. Okay, otherwise, that's it for this video. That's some decent examples dealing with springs. All right, so feel free to try some out of your assignment. Otherwise, we'll have another video coming with some fluid dynamics problems. Okay, all right, so hope you're having a good day, and we'll see you soon.